Welcome back to the classroom. This is Mr. Wong going through another physics problem. This is from the additional sample physics paper uploaded by NESA, question 17, worth 3 marks. This is going to cover module 5, which is on advanced mechanics. We have a rocket carrying a satellite launched from Earth. So if we want to draw that out first, from Earth, we launch a satellite. Well, we can draw the rocket first. Okay, and on the rocket, we're carrying a satellite. So that's kind of what we're depicting here. Once the rocket is switched off, the satellite continues in an elliptical orbit. So at some point, if we draw a second diagram, this is our planet, and then we have our satellite that orbits the Earth in a elliptical shape. It says in this question we are to explain the changes in energy of the satellite during this journey. So I guess what we can look at is firstly, what type of energies do we see during the launching phase, and what do we see during the orbiting phase? So that's what we want to look at. Okay, so let's firstly address this one here. What type of energies do we have at launch? Well, obviously what we have is kinetic energy, because the rocket is moving from a position of 0 velocity to whatever velocity we get at whatever point. It is accelerating because there is a force or thrust pushing it forwards, and that's actually due to the engine or the fuel that's burning up chemical potential energy. So we have the chemical energy. So we have energy that is from the chemicals, the fuel, and obviously as the rocket moves away from Earth, it is increasing in its gravitational potential because the gravity of Earth can pull this rocket down. So we have gravitational potential energy as well. So 3 types of energy sources that we have here. Obviously, just to take note, the chemical energy component is part of the potential in that sense, but not our gravitational potential. Okay, so there is that. If we look at the energy total, that's the add up of the kinetic energy plus the potential energy, in this case, the gravitational potential. Okay, so what we're actually seeing here is as we burn the chemical potential, okay, this energy source here, this kinetic energy source is increasing. Okay, so as the trip of the rocket continues after launch, chemical of the fuel is being burnt up. That increases the kinetic energy as we have a constant force. I assume it's a constant force, pushing it up, which means there is acceleration. And as we know with acceleration, that also increases our velocity. Okay. So that's what we're dealing with there. So we have that's due to an increasing force, or that's due to a force that applies an acceleration, which means we have an increasing velocity there. Here, on the other hand, with the gravitational potential, we can say gravitational potential. I don't know why I wrote that the other way around. As the kinetic energy is increasing, you would assume that maybe under normal circumstances, gravitational is decreasing, but that's not the case here because our rocket is moving further and further away from the planet. And by the definition, there are 2 that we can look at. There's mgh, or half, or negative gm over r, in which both scenarios would demonstrate that the gravitational potential is also increasing. So if the kinetic energy is increasing and the gravitational potential is increasing, then the total energy of this particular journey, the launching journey, is also increasing. So that's what we can conclude from that analysis there. Okay, we will eventually come back to just writing a written response for this, but for now let's just go with like a little sort of diagram to go through it. Now onto this one here. So now we're in orbit. If we're in orbit, that means there is no more fuel used. If we're not using any more fuel, it means we're not converting more chemical energy into kinetic energy anymore. So now what we do expect is that the total energy is now going to stay constant or the same, which means whatever happens to our kinetic energy, the inverse effect will occur for our gravitational potential energy. Okay, so if you recall, there are two positions that kind of nicely depict where we get maximum kinetic and gravitational potential energy. So we have this spot here, and we have this spot here. Okay, so the spot where we're closest to, I think we called that the pedigree. Let's just check that really quickly. Okay, so I pronounced it technically wrong, but this is the perigee, and over here we have the apogee here. Okay, so when we are at the closest point here, we expect that the kinetic energy will be at its maximum point, and we expect the gravitational potential to become a minimum value. Okay, the reason being is as the satellite approaches towards the perigee, we already discussed the formula for gravitational potential, but as this r gets smaller, so that distance that we have here gets smaller, the value of the potential energy becomes more negative, so it's decreasing. So this is the point here. Over here, obviously, it's at its maximum point. The formula to represent kinetic energy, if you recall, is mgm over 2r. That's the relationship between kinetic energy and gravitational potential. So at its smallest point here, right, we will see that kinetic energy is at its maximum point, and over here it will be at its minimum point. The other way we can also demonstrate that is the gravitational pull from the planet on the satellite is weakest here, so there's lesser force, lower acceleration, whilst here we have the maximum force, maximum acceleration, so maximum motion as well. So that's a nice little scribble to go through how we'll approach this question. What I'm going to do now is I'm going to put this into words. Okay, with a bit of transition, we're back to a blank-ish response. So we're going to talk about this during launch or at launch, and we're going to talk about it when it's in orbit. So what we know is at launch, the total energy, or the energy total, is increasing. Okay, and that's because the kinetic energy is increasing due to the chemical energy of the fuel as the rocket leaves. So as the rocket moves further away from Earth, gravitational potential increases as well. Okay, so here we explain why the kinetic energy is going up. It's due to the transformation of chemical energy. So due to transformation of chemical energy of the fuel, and as the rocket is moving further away from Earth, we also get an increase in gravitational potential energy, which leads to the energy total also going up. Okay, so during orbit. Okay. So during orbit, what we know is we already said that the energy total, or the total energy, will remain constant. Okay, so that's what we get there. What we also know is the two wording. So we also know is constant as no more fuel is available to what can we say, launch the rocket faster. Okay, so now we have a sort of motion where the rocket is no longer being propelled, and now it's in orbit. Launch faster, or we'll say further, and now in an elliptical orbit. Okay, what we know is at the perigee, so I might just fix that up. So at the perigee, the kinetic energy is maximum and the gravitational potential is at its minimum. Okay, what we could say is as the planet is moving, then, or as the satellite is moving away from the planet, we'll see an inverse change between the two, or the two will swap over with each other. So that's what we can say. Okay, so as the satellite moves away from Earth, kinetic energy will go down and gravitational potential energy will go up. And what we'll find is at the apogee, kinetic energy is at its minimum point and gravitational potential is at its maximum. Okay, so that's what we have there. So what we can say, I'll just summarize really quickly. During the orbiting phase, because the energy total is constant, because there's no more fuel to launch our rocket further, we get this satellite now in an elliptical orbit. So what that means is as the kinetic energy is changed, gravitational potential needs to change with it. So there is a distinct relationship between the two. We already said the energy total is equal to kinetic energy plus gravitational potential. So if this goes up, this must come down if this is constant. Okay, so that's the relationship that we demonstrated here. We also mentioned that during the launch, the total energy on the rocket is continuously increasing. One, because as we move further and further away from the planet, gravitational potential is going up, but also because of the energy from the fuel that's being converted into kinetic energy, and so that's the reason why total energy goes up in that case there. If you found it useful by means where we actually draw sort of the explanation first before we get into a written response, please give this video a like and subscribe, and I will see you next time. Hopefully you enjoyed this explanation about energy changes in rockets and satellites.